You've started learning about Bohr's model of the atom and how it connects to light. Bohr's model of the atom says that the electrons can be in shells, and these shells are numbered using n. So the shell closest to the nucleus is n equals 1, the third shell out is n equals 3, etc. Generally, it's considered to go up to about 7. Theoretically, it can be infinite. The idea is that anytime we move an electron this way, it's an energy input. It requires energy to do so. But when an electron falls back down, we get an energy release. And when energy is released, that energy releases as a photon of light. So one of the things that you do is you calculate the energy required for an electron to move up shells or the energy released when an electron moves down shells. And the equation that you use to do that is this. The change in energy equals Rydberg's constant times 1 over the initial shell squared minus 1 over the final shell squared. You're going to need to know the value for Rydberg's constant in order to do this. The value for Rydberg's constant is 2.18 times 10 to the negative 18th joules. So this value comes out in joules, the amount of energy that it takes for one electron to do this, or joules per photon. So for example, if we have an electron that falls from the fifth to the second shell, and we're going to find the energy emitted. I know that I'm looking for the change in energy. My initial shell, Ni, is 5. My final shell is 2. So the change in energy is going to equal RH, which is 2.18 times 10 to the negative 18th, times 1 over 5 squared minus 1 over 2 squared. In my calculator, 1 over 25 minus 1 over 4, I get that answer, and now I multiply by 2.18 times 10 to the negative 18th. And I get the change in energy to be negative 4. I'm going to round here, 6 times 10 to the negative 19th joules. If you think back to thermochemistry and what negative energy means, that means exothermic. So in this process, when an electron's falling, 4.16 times 10 to the negative 19th joules of energy are released. One of the other things you'll be asked is what wavelength of light corresponds with that. So when an electron falls and energy is released, that energy is released as a photon of light or a particle of light. And some equations that you use when you're applying to light are this and this. The first one is energy is proportional to frequency. The Greek letter nu is the frequency. It's in cycles per second or hertz. Higher frequency light has a higher energy associated with it. H is also a constant. H is a constant known as Planck's constant, which is 6.63 times 10 to the negative 34th. Another equation that we use, and this units on that are joules seconds, if you care. Another equation we use is C equals lambda nu. C is the speed of light, which is 3 times 10 to the 8th meters per second. Lambda is the wavelength, and that's in meters. And again, nu is still frequency. It can also be convenient to solve these two equations simultaneously. If I rearrange the second equation for frequency and plug it into the first equation, I get this. So I could shortcut it and not have to find lambda first if I was ultimately looking for the wavelength. So let's take a look at a problem that involves both. An electron falls from n equals 6 to n equals 2. Find the wavelength of light emitted. So the first thing I'm going to need to do is I'm going to need to find the energy. I'm going to find the energy by using this equation. Once I find the energy, I can then use this equation to find the wavelength. So solving. 2.18 times 10 to the negative 18th times 1 over the initial shell squared minus 1 over the final shell squared. I'm going to get a negative energy value here because I know energy is going to be released. So 136 minus 1/4. That answer times 2.18 times 10 to the negative 18th joules gives me negative 4.84 times 10 to the negative 19th joules, or 4.84 times 10 to the negative 19th joules are released. When I plug energy in here, I'm going to plug in the absolute value of it. Otherwise, I'm going to get a negative wavelength, and negative wavelengths aren't a thing and don't make any sense. So substituting in, excuse me, to the equation on the right, 4.84 times 10 to the negative 19th equals, I'm going to run out of room. Let me rewrite this. So plugging into the equation on the right, we'll have 4.84 times 10 to the negative 19th equals h times c over wavelength. H is Planck's constant, which is on the previous slide, and is 6.63 times 10 to the negative 34th. And c is the speed of light, which is 3 times 10 to the 8th. I'm going to run out of room, so I didn't write it in regular scientific notation. So solving, I'm going to do 6.63 times 10 to the negative 34th times 3 times 10 to the 8th divided by 4.84 times 10 to the negative 19th. And I get wavelength to be 4.11 times 10 to the negative 7th meters. If I wanted to convert that into nanometers, I could, and sometimes you'd be asked to. I'm sure you can look up that conversion if you need to. And there's the wavelength of light.